In our course, we've learned much about our solar system. We explored the terrestrial worlds, the Jovian planets and their moons. We looked at smaller bodies such as asteroids and comets. And we even learned about Pluto and the Kuiper Belt. So we've gotten a nice introduction and overview of our solar system. Now, up until just very recently, though, ours has been the only solar system we've been able to analyze and learn about. Well, that has now changed. Astronomers have now found planets around other stars. This has been a profound question for centuries. Are there other planets in the universe? And we now know the answer is yes. So this gives us a much broader view of planetary systems rather than just studying one, ours. We can now study others, we can compare them and contrast them to what ours is like and learn so much more not only about them, but even about ours. So how do we find planets around other stars? Well, the stars are quite far away and as a result quite faint. And if they're faint, you can imagine that their planets are extraordinarily faint and extraordinarily difficult to try to take a picture of. So astronomers have had to utilize indirect methods to identify these planets. We're going to look at two of these particular methods and see how they've enabled us to again discover and even investigate other planetary systems. Our first method begins with gravity. You think about the gravity of a star, we normally think of a planet orbiting around the star, but that's not quite exactly correct. Planets also have a relatively small amount of gravity, and that affects their star. So in other words, it's not just that the planet is going around the star, but rather both are going around the center of mass of the two of them. And therefore the star has a very slight circular motion. Now if we're able to detect that motion, we would be able to infer the existence of a planet around that star. And so we might think of the stars having a very slight little wobble. Now for decades astronomers looked for this wobble. They tried to see if they could measure the positional change, but it was very, very difficult and they were not really able to do that successfully. Consider, for example, if we were to look at our sun from a great distance, not knowing whether it had planets or not. We're going to consider just briefly Jupiter as the largest planet. It would cause a slight wobble in the sun's motion as Jupiter orbits around it. Well, how could we then detect that motion if we don't see a positional change? Well, here the answer deals with light. We take the light from a star and we break it into a rainbow or a spectrum. And as we look closely at that spectrum, we're going to see certain lines in that spectrum that indicate the star is emitting light at certain wavelengths. Now we can measure those wavelengths here on Earth because we know, for example, different elements give off those different wavelengths in the star. So for example, if we thought of perhaps hydrogen or helium gas giving off certain wavelengths, and we saw those wavelengths in a star, we'd know the star has those elements. We'd also know the exact wavelengths that they normally give off. Well, here's where a technique called the Doppler shift comes into play. The Doppler shift means that if a body is moving towards us, its light waves are going to be slightly shortened. They're going to be a slightly shorter wavelength, which to you and me would mean they're slightly bluer. Now we may not be able to see that with our eyes, but the effect is real. In contrast, if the object was moving farther away from us, moving at a certain velocity, we would see the light waves ever so slightly stretched out to a longer wavelength. Well, we now have the technology to measure those very slight shifts, and as a result, we're able to measure when a star has a slight motion towards Earth and away, towards and away, as a planet is affecting it. This then is the key to the method. We detect these very slight shifts in the wavelengths of the light in the spectrum. And these shifting wavelengths over time, hours, days, weeks, tell us there's a planet orbiting that star. Well, this technique then was implemented back in the early 1990s. Different teams were trying to measure this effect, and success followed shortly thereafter. You can see in one diagram that various positional measurements were made showing a periodic motion. In other words, the star was indeed moving towards us for some time and then away from us and then towards us and away from us. Now when you actually measure the amount of time or period that it takes to do that, the motion of the star, its period, is going to be equal to the motion or period of the planet. And as a result, as you can see in our diagram here, we can find a planet that in this example has a period of about 4 days. You also see a very simple mathematical equation here. This is called Kepler's third law, and this relates the period, or P, to the distance that the planet is from its star, the A. And so as a result, if astronomers measure the amount of time, or again period it takes for it to orbit, they can pretty well determine the distance of the planet. In this case, there was a bit of a surprise. This particular planet only took 4 days to orbit its star. That's quite short compared to the planets in our solar system. As you know, Earth taking 365 days. Well, besides the period, if we are carefully making these measurements over time and we plot these out, we can also measure the amplitude of the shift. What is this going to tell us? Well, it's going to essentially tell us how much the star is moving, but that is directly related to the mass and gravity of the planet. So if we see a very small amplitude, we have a very low mass planet, but if we have a greater amplitude, a very high mass planet. So already we're able to determine some basic fundamental properties of a planet that we can't even see orbiting a star. So this method has been extremely productive. Many hundreds of planets have now been found using this Doppler effect, showing us the radial velocity of the star. Well, shortly thereafter, astronomers began to employ a second method, and this is called the transit method. Here we have a situation where we might have a star with a planet orbiting it, and as the planet passes between the star and Earth, it's going to block some of the light. Now, this is again a very subtle, very small effect. Planets are quite small compared to stars, but if we measure carefully the light output of the star, we would see a very slight dip over time while that planet passed in front of the star. We would expect, of course, that the planet would eventually go all the way around the star and then come back and block the light again. So once again, if we were to time between these transits, we would know how long it's taking the planet to move around the star. Already understanding, again, the period of its orbit, once again, would give us its distance. Now again, this dip is very small, often perhaps only 1% of the light, or sometimes even less, but the amount of the dip, in other words, the depth, how much light is being blocked, gives us a first good idea of the size of the planet. Is it a small planet blocking the light, or is it a larger planet blocking the light, as you can see in our diagrams? Well, we can go further. Astronomers are very resourceful, and if we know then the amount of time it takes to go around the planet, we can figure out the distance, and we can figure out the velocity of the planet. We can now measure how long it takes it to transit in front of its star. This also will give us the radius of the planet. Once we have radius, we have volume of a spherical planet, and once we have the volume, and add to that the mass that we have found from the amplitude of the shift, we now have the density of the planet. So you can see how astronomers can gather some very subtle observational data and use those to gradually build a picture of this planet that we cannot even see. So what have we found? Well, many of the early discoveries were very massive planets because they were somewhat easier to detect, but over time as our techniques have improved, we have found planets with smaller and smaller mass. Starting out with those perhaps even more than Jupiter, we've worked our way downward and now find planets with roughly the mass of Earth. So we know that there are planets of varying masses in various star systems, some very massive, some not so massive. You can see a couple of graphs here showing us, again, those masses, and interestingly, it now appears that smaller planets are more common than larger ones. This, of course, begins to get us curious. What could be on these smaller planets? Are some of them terrestrial in nature, like Earth? And this, again, has profound implications, doesn't it? Well, that all sounds very great that we can detect these planets, we can begin to learn about their properties, but wouldn't it be nice to actually take a picture of one? Well, as I mentioned at the outset, that's extraordinarily difficult. Here you've got an extremely bright star and a very tiny little planet only reflecting a very tiny bit of light towards Earth. And so it's been extraordinarily difficult. Now, astronomers have also pursued techniques to try to allow us to image stars with planets. Sometimes we can use different wavelengths, for example, infrared light, in which the star doesn't appear as bright as it might in visible light. But in infrared light, a planet might appear a little bit brighter than it would in visible light. So in other words, the extreme difference in brightness is somewhat lessened, as you can see in our pictures here. We also have found in some stars disks of material orbiting around them that have not quite finished forming planets. We learned earlier that it takes time for these disks of material to form planets, and yet this tells us that our understanding about our solar system was likely correct. Well, in a very historic, extraordinary case, the Hubble Space Telescope has actually been able to image a planet around another star. Here you see a picture taken a few years back by Hubble around a nearby star. Now, the star's great brilliance means that they have electronically subtracted some of that out so that it's not overwhelming the picture. Well, interestingly, you see a faint ring here, don't you? This ring, again, is material orbiting the star, various, we think, planetesimals that we discussed earlier, and they are forming planets. Well, through very careful analysis, you can see through a close-up image that one particular one appeared somewhat larger and brighter than the others, and essentially we saw it moving in orbit around the star. So this is an extraordinary result here from the Hubble Space Telescope, allowing us to watch a planet move around its star over a course of a number of years. Others have attempted to do this similar thing from the ground, using ground-based telescopes to try to look for planets around other stars, and there have been some successes. As you can again see in some of our pictures here, we work to reduce the light of the star, but preserve the light of the planet. And here again, some very extraordinary images. You can see a few small dots of light near these stars. And the rightmost image, actually 3 planets. And pictures taken over a number of years show their motion around their star. So it's a very exciting time for astronomers to be finding and exploring and analyzing planets around other stars. Well, besides looking at individual planets, what have we found? When we step back perhaps and look at an entire star system, well, no surprise, ours has 8 major planets and a number of other smaller bodies, and sure enough, other systems as well have multiple planets. Here you see some examples of a few of them showing, again, how they compare to ours. Our Sun's system at the top there showing the different inner planets and their distances. Notice something very interesting here. Not only are there multiple planets around these various stars, but you can see the scale indicating their masses are quite large. Now, we said earlier those are much more easy to detect, but what I really want you to take note of in this diagram is the fact that there are some very massive planets very close to their star. This was a major surprise when astronomers began to uncover this and began to see that some stars have very massive, very large planets very close to them. You see that in our other diagram here as well. So this was a major surprise, very different from our solar system. It's as if we had a certain idea of what a solar system looked like, but now we saw a much greater variety. Very much like if you were to simply interview or analyze one human, you might get a certain idea of what human beings are like. But on the other hand, if you interviewed hundreds, you'd get a much broader understanding, wouldn't you? You'd learn so much more. This is essentially what is happening today with extrasolar planets. Well, when we consider these very large, massive planets close to their star, that seems to be a problem, doesn't it? Didn't we discuss the fact that large planets, at least in our solar system, form at greater distances from the sun, didn't they? Why was that? Well, we talked about the fact that they needed to be out beyond that frost line. They needed to be out farther away where ice and gas were not vaporized, but were in great abundance, and therefore the planets could grow much larger. We said inside that frost line, you don't have the ice and the gas, and you essentially end up with less massive, smaller planets. So this was a very interesting problem that arose as we began to discover these large planets orbiting very close to other stars. How could you explain that? Well, these became known as hot Jupiters, so to speak. We picture a large Jupiter-type planet orbiting in close, or would be very, very hot. So again, if they can't form there, how'd they get there? Well, ultimately the answer became clear. Planets can actually change their orbits. That was something that we really hadn't considered in the past. We looked at our solar system and we assumed that the planets formed where they are and have stayed where they are. But clearly these other planetary systems were telling us that simply couldn't be the case. Their planets had to have moved orbits. In other words, their larger planets would have had to form beyond the frost line, and yet here they are closer to their sun. How do you move a planet? That's a very challenging idea. Well, scientists got busy at work and have identified at least two major ways that this can happen. The first is called planetary migration. Now this would typically happen more often in the earlier stages of a solar system. We discussed how our solar system had this flattened disk of material from which the planets were accreting. And as a planet would accrete and get more massive, its gravity, of course, would pull in more objects, and it would tend to clear out a space in its orbit. Well, picture now this planet orbiting kind of a cleared out region, and yet the rest of the disk, still out beyond the planet, has maybe not finished forming. Well, all of the matter out in that disk has a considerable amount of gravity, and if it's farther from our planet, it's going to have an effect on its orbit. It's going to essentially rob it of angular momentum, and our planet is going to steadily work its way inward. So you can see where we're going here. Imagine now a large gaseous planet forming, clearing out a gap, and yet the remaining part of the disk forces it to move inward closer to its star. So really, a very profound insight into how solar systems can change. Well, once that disk dissipates, we might not think it's so possible for that to occur, but there's another method to move a planet. We call that gravitational encounters. Now envision several large planets in a solar system, and over long periods of time, very slight gravitational disturbances might move them to a position where they get closer to each other. And of course, the closer they get, perhaps the more their gravity affects each other. Well, in the right kind of situation, you can have two planets approach close enough that yes, one would pull on the other and perhaps eject it out of the solar system, but in the exchange of energy, that first planet now would need to fall inwardly. Now we may come along millions of years later and never even know about the planet that was ejected, but we do find a planet much closer to its star than we might normally expect. So yes, gravitational encounters can have a dramatic effect on the orbit of planets. This may happen, so to speak, all at once with one major event, where two planets get very close to each other and one is violently thrown out and one is violently pushed inward, or this could happen more gradually. Picture now, for example, as we talked about in our solar system, perhaps numerous smaller bodies, perhaps like we saw in the Kuiper Belt. And over long periods, if these smaller bodies approach the larger one, yes, the smaller bodies might be ejected outward, which we learned might be a basis for an Oort cloud, but the large planet might move just very slightly inward, and very slightly inward, and very slightly inward. But if that was repeated many, many, many times, that large planet could migrate inward. So I think you can see that there are some valid possible ways that you can move planets. And again, the point is we had a very static understanding of our solar system for decades, even centuries. We had a very big assumption there, didn't we, that our planets formed where they are and stayed where they are. And it seems that our planets have not moved too much. That's not entirely wrong. But in other planetary systems, we have seen clear evidence that planets have moved orbits. Well, as astronomers continue to find more of these planets, some large, some small, natural interest might be in Earth-like planets. Could there be planets out there like Earth? Well, we'd want to start out, of course, looking for planets of approximately the same size and the same mass. But if we were interested in one that might be hospitable for us to go visit, certainly we'd want it to be at the right distance from its star. We wouldn't want it to be too close where it'd be very, very hot, or too far where it'd be very, very cold. So the search for Earth-like planets has gained great impetus, great momentum in recent years. And it's exciting to find out that, yes, indeed, we are finding Earth-sized planets, Earth-mass planets, in approximately the right distance from their stars now, that it would be a hospitable environment. We call that distance the habitable zone. Now that term may be just a little bit optimistic. Just because a planet is in this habitable zone does not necessarily mean there's life there. All it does mean is that temperature is correct, that you and I could probably go there and not be too hot or too cold. Essentially, astronomers have settled on the definition of saying, could liquid water exist? If we were in that range where liquid water could exist, not being frozen or not being boiled away, well, that would be a nice range for us. So this distance from a star where liquid water could exist is now known as the habitable zone. And we've again begun to start to find a few examples where this appears to be the case. How have we done that? Well, primarily by means of the Kepler spacecraft. Kepler has been in orbit now for a number of years. It's surveyed thousands of stars, and it's watched very carefully and very precisely for those very slight changes in light that would indicate a transit of an extrasolar planet in front of its star. Well, once those are identified, then astronomers on the ground can turn their giant telescopes to analyze that system in more detail. And as a result, we have found quite a number of fascinating systems. So you may want to take a few minutes and go out and explore what the Kepler spacecraft has done for us. I'll give you the short results here, kind of the summary of it. Some very exciting results. To date, Kepler has found over 3,500 extrasolar planets. That's a remarkable number when you consider. When you look at that number, it's just becoming big enough to begin to start to do some statistical analysis. And it now looks that approximately 50%, or 1 out of every 2 stars, on average, has an extrasolar planet. So that in itself is, again, a very profound result. Our galaxy is teeming with planets because we know there are many, many, many millions of stars. Well, how many of those might have planets roughly like Earth? It seems now that number is perhaps about 10%. So that might not sound like a lot, but 10% of millions of stars is still an awful lot of planets. You see in one graph here that smaller planets seem to outnumber larger ones. So again, very exciting times for astronomers to be going out and not only identifying extrasolar planets, learning about perhaps a few individual specifics, but now stepping back and getting statistically sufficient numbers to get an idea how common are planets in our Milky Way galaxy. So this leads us to a few big questions then, doesn't it? We just touched on this first one. How common are extrasolar planets? It seems that somewhere approximately 50% of sun-like stars have planets, 1 out of every 2 on average. Now some may have more and some may have none, but the point is there's a lot of extrasolar planets. When you consider perhaps so many billion stars in the Milky Way, again, you come back to so many billion planets that are out there. How common are they systems like ours? Well, it seems like ours is a pretty friendly system for life. It doesn't surprise us. But there's a fair number, perhaps 20 to 25%, that are relatively hospitable as well. Sometimes we know that planets have migrated inward now, some perhaps even outwardly, and so you get some disruption there in planetary orbits, but it does seem that there are some that are going to be relatively hospitable. Finally, how about Earth-like planets in that habitable zone? Many are very interested in such a question. In other words, could there be planets similar to Earth? It seems that planets in habitable zones are about 1 out of every 50, or about 2%. And again, that may not seem like a big number, but when you multiply that by millions of stars, you begin to get an idea of the exciting possibility that there could well be planets out there that are hospitable. Now, I want to emphasize that just because a planet is in that habitable zone, as I mentioned earlier, it certainly does not mean there is life there. It simply means the environment would be hospitable to life. There might be, but on the other hand, there are many other factors that we don't have time to go into in this course besides simply temperature and mass. There's factors like, for example, atmosphere and others that would come into play. Think for a moment, we might say, had we observed our solar system from a great distance, we might look back and say, well, look at, there's Venus and Earth and Mars. They're all pretty close to that habitable zone, but you and I know Venus is not habitable. And today, Mars is not. So the point being, again, it's a good first step, but it doesn't tell us if there's life there. Well, it's been quite an interesting investigation of extrasolar planets. Let's go ahead and summarize what we discussed. We found 2 primary ways that extrasolar planets are discovered. We talked about the Doppler shift, where the planet's gravity causes the star to have a very slight motion towards us and away from us. We can measure that motion precisely and find out various properties of the planet. We also talked about how transits occur, where a planet passes between us and the star and blocks just a little bit of light that also betrays the presence of the planet. We did see just a few pictures of actual planets because it's extraordinarily difficult, but as time goes on, you can be sure astronomers will continue to push hard to improve our ability to image extrasolar planets. What have we learned? Well, we can now talk about things like the mass, the size, the density, the temperature, and very soon here probably the composition of these planets. We'll get to know them much better. We have already found a very wide variety, a range, so to speak, of planets. And we also saw these hot Jupiters teaching us that planets can change orbits. Number 1, planetary migration. Number 2, gravitational encounters. So it does really show that solar systems can be much more dynamic than we originally thought. Finally, we looked at the very exciting results from the Kepler spacecraft that have given us a first good statistical group of planets with which to examine. So again, exciting times learning about extrasolar planets. Well, I hope you've enjoyed our course. Again, we've learned much about our solar system, and we wrapped up today with an exciting look at other solar systems. I thank you for joining us and hope to look forward to seeing you in our next course.